Okay, so let me start by saying to everybody that I'll try to pay attention to the chat. So you can ask questions in the chat, and then I'll try to point them out to you, Deeksha, if we get
Okay,
some
yeah.
along the way.
Sounds good. Yeah.
And yeah, if people have a long question, maybe we leave it to the end, and we can even put you on stage if you want to ask a longer question then. So you can do it by audio. Other than that, let me just say thank you to Deeksha for agreeing to talk to us. Deeksha has done a lot of work in her PhD on optimizing higher order smooth functions. And today we'll see kind of a paper that makes this into quite a general method. I think it's a fair way to characterize it. So thank you, Deeksha.
Oh, thank you. Thanks for the invitation. So today I'll be talking about one of our recent papers, which is on width-reduced methods for quasi-self-concordant optimization. So this paper is joint work with Brian Pullins and Sushant Sachdeva, and it's about to appear in Europe 21. So I'll first define these terms, quasi-self-concordance and width reduction, before we look at our algorithm. Okay. So by quasi-self-concordance, I mean you consider a function and you consider any 2 points, x and y. And if x and y are close enough, we want the Hessian of the function at x and y to be off by a factor of at most e to the nu times r, where nu here is a fixed parameter for the function, and we call it the quasi-self-concordant parameter. So if a function satisfies this property, we say the function is quasi-self-concordant. And there are a bunch of interesting functions that are widely used, which are quasi-self-concordant. So let's look at a few examples. So consider this function, which is a sum of exponentials. So you have e to the xi by mu for some parameter mu. And this is quasi-self-concordant with parameter 1 by mu. And we'll see that this function is actually almost directly related to softmax and infinity regression. And as a result, it's also related to max flow. Then the logistic regression function is also quasi-self-concordant with parameter 1. And LP regression or regularized LP regression is also quasi-self-concordant for all p greater than 2. Okay. So we'll see how we can relate the sum of exponentials to softmax and infinity regression. So it's just, if we look at these objectives, if you look at softmax, it's essentially just the log of the sum of exponentials. And in this case, if we consider the problem of minimizing the sum of exponentials and minimizing softmax, they have the same minimizer. And if we also note that both these functions are quasi-self-concordant and they have the same quasi-self-concordant parameter. So we'll also note that softmax is a good approximation to L infinity regression. It's like a smooth approximation to the infinity regression function. So if we look at these two objectives, like the infinity norm objective and the softmax objective, we can actually relate them as follows. So the infinity norm objective is at most the softmax at x, which is at most some 2 mu log m plus the infinity norm at x. Now, if you actually choose the softmax parameter to be epsilon by 2 log m, then you can see that the infinity norm of x and softmax at x are off by at most an epsilon. So you could actually minimize the softmax function to obtain an epsilon approximate solution for the infinity regression problem. And as we saw that softmax and the sum of exponentials had the same minimizer, it's sufficient to minimize the sum of exponentials for this particular value of mu to obtain an epsilon approximate solution for the infinity regression problem. And as infinity regression captures the maximum flow problem, you could use the sum of exponentials with this mu value to obtain a maximum flow algorithm. Okay, so let's first define our framework. So we're interested in these univariate functions, and when you apply these to a vector, we just want them to be applied coordinate-wise and you sum them over. And we're interested in the problem of minimizing f of x under some subspace constraints, ax equals b. So here F is quasi-self-concordant and A is a short fat matrix. So AX equals B is an underdetermined system. You can also actually replace X by some C times X for some matrix C, like a tall, thin matrix C. And our algorithms will work for those cases too. But for now, we'll just focus on this case of minimizing f of x for simplicity. Okay. So width-reduced methods. So this was first, these are actually multiplicative weight update routines, which is a special step, which we call width reduction. And mostly each iteration in these algorithms, they involve solving a system of solving a weighted linear system where these weights are related to the weights of the multiplicative weight algorithm. And it has been seen to improve the convergence rates from m to the 1/2 to m to the 1/3, where m is the size of the input. So this extra step of width reduction can improve these rates. Otherwise, the normal multiplicative weight update routine, assuming that converges in m to the 1/2 iterations. And this was first seen in the context of max flow in this paper by Cristiano, Kellner, Madri, Spillman, and Teng in 2011, where they were able to use this width reduction to, on a graph with n vertices and m edges, to converge in m to the 1/3 iterations. So there have been several other works where we have seen this kind of width reduction to obtain similar improvements, like m to the 1/2 to m to the 1/3. So it was first seen in max flow, and then it was seen in infinity regression. So matrix scaling, so in this work in 2017, they modeled matrix scaling as a sum of exponentials and softmax, and they were able to use this width reduction scheme here as well to go from m to the 1/2 to m to the 1/3. In a recent work, we show that for LP regression, even for LP regression, you can do a similar thing and get m to the 1/3 iterations. And in 2019, Ian and Platu show this for L1 and L infinity regression. So in the LP regression work, that works for p greater than 2. So in all of these works, they do a similar improvement from m to the 1/2 to m to the 1/3. But their analysis are very tailored to this function in use. There's no idea of why this is working or where all can you apply this technique to. And yeah, so the main contribution of this work is to actually provide a unified analysis for this width-reduced multiplicative weight update routine. And we can extend this to all quasi-self-concordant functions. So for some of the important functions that we listed, that is sum of exponentials, LP regression, and logistic regression, we get the following rates of convergence. Okay, so we have the following setup: minimize f of x under the subspace constraints, and we had f as quasi-self-concordant. So we now add an additional assumption that the optimizer of f satisfies this infinity constraint. The infinity norm of x star is at most 1. And we have two parts to this algorithm. So in the first part, we just given any epsilon and quasi-self-concordant f, our algorithm can return a vector in at most m to the 1/3, epsilon to the -5/3 iterations, so that this satisfies the subspace constraints and the infinity norm of x is bounded. So you should think of this bound as a constant, or we'll see that in the case of infinity regression, it's actually 1 plus epsilon. So further, once we have this solution, we show that for other functions, we actually give a boosting algorithm, which uses the solution as a starting point, and it converges to a point so that the f of x is at most 1 plus epsilon times the optimum of the function. And the rate of convergence here is log 1 by epsilon. But this first part is actually sufficient to obtain an epsilon approximate solution for infinity regression. Okay, so we had a quasi-self-concordant function and the optimum satisfies this bound. So the algorithm, so first we'll just see a simple algorithm without any width reduction, just a simple multiplicative weight update scheme that actually converges in m to the 1/2 iterations. So you start with some solution, some set of weights, and for some parameter tau, and we'll look into what we mean by tau in a bit. But for you, basically, we want to solve a weighted linear system at each point. So these linear, so let's think Ri is essentially the weights of the weighted linear system you want to solve. So it's the second derivative of f and some small regularizer term. And we are solving this linear system at each iteration, which is just a weighted system defined by these weights R. And we use the solution returned by the system to update our current x and our weights. And in the end, we just returned x, right? So this algorithm, it actually requires some order tau iterations. If you see, we're running this while loop some tau number of times. And tau here is basically the width of the algorithm. And by width, we mean it's a bound on the infinity norm of the solution that's returned by this weighted linear system that we're solving at each iteration. So if this is the only algorithm we have, we'll show that. So it's easy to see that this width is at most some square root m. So if you just look at this at this term here, since R is a sum of both terms and f is a convex function, so quasi-self-concordant also actually implies convexity, which is something I didn't mention. So you could just use this term to lower bound this Ri delta I squared. And this is a bound which we prove in the paper, and I won't get to how we prove that. And from here, it actually, if we just use this part and this part, it follows that the L2 norm of this vector that is returned by this weighted linear solver is root m, is at most root m. And so the infinity norm is also bounded by root m. So we get the rate of convergence to be root m by epsilon. Okay. So now we want to improve this. So another way to think of this is at each point, if we want the solution to be about a constant, and at each point you're adding something that has a value at most root m. So you'll need about root m iterations so that it averages out back to around a constant. So now in order to improve this from m to the 1/2 to m to the 1/3, we have a special thing called width reduction, and we'll look at that now. So we consider this a similar algorithm. You have the same starting point, same set of weights. We are solving the same linear system at each iteration or same quadratic problem. But now we have a threshold tau. Now we'll think of tau as some threshold. And if the solution returned by this linear system has an infinity norm bounded by this threshold, only then we're updating our solution and our weights in the way we were. Otherwise, we just look at the edges, look at the coordinates which do not satisfy this threshold. And for those coordinates, we just want to increase the resistances by a factor of 1 plus epsilon. And we're returning the same solution. So here we call the first set of steps as the flow steps and the second set of steps as the width reduction steps. And you see the number of flow steps here are still tau by epsilon as we had before. The number of width reduction steps will show in a bit that these are bounded by tau. And if you actually set tau to be m to the 1/3, this gives us our convergence rate. So in some way, we are enforcing a width on this algorithm. Earlier, we just had this bound to be m to the 1/2, so we needed m to the 1/2 iterations. Now we're enforcing this width. And the reason we could actually enforce this width is because the additional number of width reduction steps that we have are also basically m to the 1/3. Okay, so our algorithm can actually be shown to return the following vector with a bounded infinity norm. And it converges in m to the 1/3 epsilon to the minus 5/3, etc. iterations. Okay, so right, so the first thing we'll show is that we actually return a solution that satisfies the infinity norm bound. So if you note the way x is updated and the way w's are updated, the solution we return is at most the final weight vector times nu, where nu is the quasi-self-concordant parameter. And for softmax and sum of exponentials, this nu is basically 1 by epsilon. Right, so the final infinity norm of the vector, at least for softmax, is the final weight vector by mu. And we will prove that this weight vector has an infinity norm at most 1 plus 4 epsilon. So since we saw that this was the sum of exponential was directly related to infinity regression, this directly implies that our solution has a 1 plus 4 epsilon norm bound. And for other functions, we actually show in our paper that this value of nu times the infinity norm of the final weight vector is at most a constant. And then you can use the boosting algorithm to obtain a solution close to the optimum. Okay, so we'll now see why this is 1 plus 4 epsilon. So in order to analyze our algorithm, we track the following two potentials. The first one is basically just the trace of the Hessian of the function, or it's just the sum of the R values that we had in those weighted quadratic system, weighted quadratic problems that we are solving. And this is the weighted quadratic problem that we're solving. Okay, so the way the analysis of this algorithm goes is, we first want to see what happens to these two potentials with every flow step and every width reduction step. And we use some relation between these two potentials. And we'll show that, so we'll first show that if we have a certain number of flow steps and a certain number of width reduction steps, then our function phi is bounded by something. And then we would show that you can't actually have more width reduction steps by using the relation between phi and the other potential psi. Okay, so if f is quasi-self-concordant, then our potential phi is bounded as follows after t flow steps and k width reduction steps. So the first part just shows that it grows like this for flow steps and for width reduction steps. And then if you actually have tau by epsilon flow steps and tau width steps, we show that you can directly plugging this in gives us phi to be bounded by by e to the 1 plus 4 epsilon times the initial value of the potential. So we have this bound. Now for softmax, if you compute the second derivative, if we actually explicitly compute phi, we have 1 by mu square times e to the wi by mu. And appropriately choosing the initial weights, you can replace 1 by mu square by the initial potential. And just using this bound gives us that wi by mu is at first 1 plus 4 epsilon, if the number of flow steps and width reduction steps are bounded by these numbers tau by epsilon and tau. So this gives us the final bound on the weights vector to be 1 plus 4 epsilon times mu. And this gives us our bound for softmax. Okay, so far we've seen that our algorithm actually returns a solution that has a bounded infinity norm. And if we consider the growth of phi with the algorithm, then phi is bounded by the initial potential times e to the 1 plus 4 epsilon. Right. So that was assuming we have some tau by epsilon flow steps and tau width reduction steps. So the next part is to show that you actually cannot have more than k width reduction steps. So after these t flow steps, this holds because the way we define our algorithm, we are assuming these many flow steps. So we need to show that you can't actually have more than k width reduction steps. Okay. So if we look at this potential psi, so psi mainly grows monotonically for a flow step. And for a width reduction step, it increases significantly. Since tau was something like m to the 1/3, it's actually increasing by a factor of 1 plus 1 by m to the 1/3 every time we take a width reduction step. Oh, sorry. Right. So, and we also note that our two potentials are also related as follows. And this just follows by using this bound. You replace this with the optimizer of the problem, and a simple math makes this inequality. Yeah, just gives this inequality. Okay, so if we want to show that we can't have more flow steps, or more width reduction steps, so we need the following inequality to hold. So this follows basic. So we had the following relations. We had that our phi was at most this quantity. We have that psi grows at this rate. And we have that psi and phi are related. So psi is upper bounded by 1 plus epsilon times phi. Oh, sorry. And then you can use this upper bound on phi to obtain this inequality. And psi is lower bounded by this quantity. Right. So for this bound to hold, we need the number of width steps to be at most tau. Okay. So this actually shows that you can't have more than tau width reduction steps. So far we showed that if for any epsilon, for any quasi-self-concordant f, our algorithm returns some x that satisfies the subspace constraint and that sort of has this infinity norm bound. Right. And this algorithm converges in m to the 1/3 iterations. And if we apply this algorithm to the sum of exponentials, then with parameter mu approximately epsilon by log m, our algorithm actually returns an x which has an infinity norm bound, 1 plus 4 epsilon times optimum. Okay. So next we want to actually see how our boosting algorithm works. So given this solution, which has a constant bounded infinity norm and which satisfies the subspace constraints, we want to find a solution. We want to find a point x that satisfies this bound, that is epsilon close to the optimum in optimum values. And we want to do this fast. So we will show that you can actually converge to the optimum at a rate of nu m to the 1/3 log m by epsilon, calls to a linear system solver. And this actually, if you combine these two, you will get an m to the 1/3 log 1 by epsilon algorithm for LP regression and logistic regression. Okay. So the main idea we use here is, if you recall the definition of quasi-self-concordance. So for any 2 points that are close enough in infinity norm, we have that the Hessians of the functions are also close enough. They're off by a factor of at most e to the nu times r, right? So using this property, you can actually give upper and lower bounds to the function, quadratic upper and lower bounds to the function for a small update step. By which I mean, if you take an update delta, which has infinity norm at most 1 by the quasi-self-concordant parameter, then you have this upper bound, which is a quadratic function, and you have a similar lower bound, which is again a similar quadratic function, just that these constants are slightly different. So we can show that if you are, we could if we are solving with this constraint box, like you have an infinity constraint box, then it's sufficient to minimize this lower bound under this constraint of infinity box, some log 1 by epsilon times to obtain to the optimum solution. So if we look at this following residual problem, or as it's usually called, a trust region problem. So you have to minimize a quadratic problem under the following constraints. So this one, the last constraint arises from the fact that this bound only holds for this quadratic bound only holds for this range. The second constraint is just from the fact that you only want to be inside an infinity box from where your initial solution lies. So inside the infinity box, the initial solution lies in. And you want to maintain the original subspace constraints, that was Ax equals b. Since the original solution satisfies the constraint Ax equals b, whatever update we add to the solution should be along the null space of A. Okay, so you can show that if you start from a solution that satisfies the subspace constraints and just solve this problem to some approximation.
Deeksha, sorry, can I ask a quick question on the previous slide?
Yeah. Okay.
So how is x changing here?
Oh, so x at each iteration, we're just updating it as x goes to x minus delta, or a scaling of delta.
So I guess I'm just, so in order to understand it seems like x is not a variable here. So if I want to understand the constraint infinity norm of x is less than 1.
Oh, sorry. Actually, this should be x minus delta infinity norm is at most a constant.
Okay. Yeah, that's what I thought. Yeah, okay.
Yeah. Oh, yeah, that's a typo. So x actually updates as x minus some constant times delta. So we want that this new iterate at xt plus 1 is also inside the also has an infinity norm at most a constant. So this should just be x minus 1 by e squared times delta. Okay. So, right. So if we just minimize this problem to an approximation, some log 1 by epsilon times, you can actually show that this converges to the optimizer in terms of solution values. And the rate of convergence is log 1 by epsilon. Okay. So, right. So it remains to solve this residual problem. So if these constraints were L2 norms instead of L infinity norms, we could just do a linear system solve and that would work out. But these infinity norms, actually, they're not smooth, so it's not very easy to directly solve them. But we actually use a similar multiplicative weight update routine with width reduction to obtain like a constant approximation to this. By a constant approximation, I mean a constant approximation to this objective value. And we again require m to the 1/3 iterations, where each iteration is solving a linear system. Oh, right. Right, so our entire algorithm, if you consider the first part and you use it to solve to a constant approximation, that requires order m to the 1/3 iteration. And the second part requires some new times mu m to the 1/3 log m by epsilon iteration. So the entire thing converges in m to the 1/3 iterations as such. Okay, so most of the previously known works for QSC optimization were based on either gradient methods or Newton's methods, and they usually obtained some suboptimum dependence on these parameters. And the most notable among all of these is the ball-oracle approach. So the ball-oracle algorithm, here they use, so in our algorithm, we were using this oracle model where we were solving a linear system at each point. Here they assume a stronger oracle. They assume that given at any point, given a radius, so let's say the radius is 1 by the quasi-self-concordant parameter. So you consider a Euclidean ball at any point, with this radius, And the oracle is that you actually can minimize the function in this Euclidean ball around the point. So they actually show that if you use the simple algorithm where you just update, so you start at a point, you look at a small Euclidean ball around it, and you minimize the function in that Euclidean ball and move to the minimizer. The simple algorithm, it converges in the quasi-self-concordant parameter, some factor r. R is the initial distance to the optimum, and log 1 by epsilon. So you could think of it as if you're covering a distance of r using a ball of some radius. So you need at least r by the radius number of balls to cover that distance, and you obtain or go to the minimizer. And you can think of this r as square root m. And for infinity regression, this directly gives a root m by epsilon iteration algorithm. So in this paper, they actually show that you can accelerate this algorithm using Montero-Schweiter acceleration. Montero-Schweiter acceleration is one of the it's one of the known optimum methods in acceleration. They have lower bounds that show that Montero-Schweiter obtains the optimum rates. And they show that you can improve the convergence from nu r to nu r to the 2/3. And this gives us an m to the 1/3 kind of iteration complexity. And for infinity regression, it gives m to the 1/3 by epsilon to the 2/3. And similarly for LP and logistic, you can get some epsilon dependence and m to the 1/3. Right. They also show that under this oracle model, where you're assuming that you have you can minimize the function in small Euclidean balls, it's optimum. This method is optimum. Right. So another thing is that this ball oracle may seem like a pretty strong oracle, but for quasi-self-concordant functions, you can actually use accelerated Newton's method to implement this. The only drawback is this requires the function to be smooth. And Montero-Schweiter acceleration does not work in the constraint setting. So this raises the main important problem that how is this width reduction method related to Montero-Schweiter acceleration? And since both of these are able to actually improve the rates on the same set of functions from m to the 1/2 to m to the 1/3. And the advantage is that width reduction is actually able to handle the constraint setting. Montero-Schweiter approach is not known to handle the constraint setting as of now. And it requires smoothness of the function. So that gives some suboptimum dependence on parameters. But, right. So to summarize, we actually gave an algorithm that, a width reduction algorithm that works for all quasi-self-concordant functions. This returns a solution with an infinity bound. And we gave a boosting algorithm that improves this. And this shows how to obtain near optimum rates for infinity regression in the low accuracy regime. Right. Okay. So thank you. For more details, you can refer to our paper. And I'm happy to take questions.
Thank you so much, Deeksha. That's very nice stuff. Do we have questions from the audience? Everybody should feel very welcome to put things in the chat. So when you, I'll ask a question while we wait. When you have this gradient term in your boosting step problem, does that just get shifted in as a linear constraint or for the multiplicative weights?
Actually, yeah. I guess you can shift it as a linear thing, but I guess you don't need to do that. you can just shift these as, so if you recall CKMST has these weights. So the weights are sort of like L2 relaxations for these infinity constraints. So the first thing is you can combine both of these infinity constraints into one infinity constraint with some center. And then you could just think of these as relaxing. You can add weights, relaxing these to be something like L2, relaxing these to L2. And you could actually directly solve this. You don't really need to move this linear term to the constraints.
Okay. So how, maybe this is not easy to say, but how is that different from the analysis that you showed before? Like it changes what phi is, or?
Right. So here actually it's a lot easier in that sense. So here you could just somehow, so these are, right. So here it becomes a lot easier. You could directly incorporate the CKMST analysis with some tweaks for some reason.
Okay.
Like the only thing here is we sort of want to maintain these constraints, and the rest of it follows. In the first part, there was a key challenge of how you update the function. So the update phi was very closely connected to, was the challenging part, and that makes both of these different, I guess.
But okay, so maybe I got lost on something then. So like ultimately, when you want to, sorry, so when you want to optimize your quasi-self-concordant functions, the high accuracy, you have to solve this problem, right? Or
right. You can. Right, but the thing is, if you want to do this, you would actually have to solve it along the null space if you have these constraints, Ax equals B. The first part, it actually works directly in the space Ax equals B. You don't go along A delta equals 0.
Okay. And then so you use the other one for what? For directly getting a lower accuracy solution, or?
Yeah. Basically, a low accuracy solution which is in the subspace.
Yeah.
If you directly had to use this, you could directly use this if you have a good starting point already.
Okay, so I can't just start with what? How bad is the dependence here on the starting point?
So the distance to the optimizer directly shows up, the infinity distance to the optimizer.
Like with a linear dependence, or?
It shows up linearly in the runtime.
Okay, so you need the other step first to get started.
Yeah. But actually for infinity regression, this part doesn't really help, and the first part directly gives you the,
Oh, thank you. That helps a lot. It looks like maybe we don't have any more questions. So let's thank the speaker. There's a way to click. Oh, wait. We do have a question now from Richard. Have you looked into neural net interpretations of these?
No, actually, I'm not even sure if what the connections would be or what it would mean.
Richard, do you want to go on stage and try to elaborate on your question?
Yeah.
Okay. Can you hear me? Can you hear me?
Yeah.
Yep.
Okay, good. Okay, yeah. So, I mean, you're dealing with softmax functions, right? Like you're getting into functions that's like, I mean, the neural net, to my understanding, is just multiple layers of like matrix and then nonlinear function, matrix nonlinear function.
Right.
My understanding, all this stuff is some form of preconditioning.
Okay.
right? I understand all this as preconditioning. So which means like you have like very strong, you're proving very strong forms of like a sequence of bad answers let me converge to a good answer.
Right.
Right. So like this stuff might have like interpretations in backprop. That's what I'm thinking.
Yeah, no, we haven't thought about this at all.
I see, but like, could you imagine like this saying something about like, is there a way to like understand like your algorithm as like a backprop type algorithm?
Yeah, I'm actually not sure. I have no idea about that, but maybe in some ways.
Okay, well, I guess I'll just have to bug you about this the next time I run into you and Sushi on this, I guess.
Yeah, no, I have no idea about this. Yeah.
Okay, cool. Thanks.
Thank you, Richard. I think we still have time for another question if anybody has one.
I guess the other one I have is like, how tight is 1/3? Like, is there a way to prove that like 1/3? Because CKMST in some very limited case, there were these examples that convince people that CKMST.
Right. So the only way we think this is tight is if the ball oracle paper actually proves a lower bound using their oracle model. But if you look at their oracle, in some ways it reduces to solving weighted linear systems. So their oracle is minimizing the function inside a Euclidean ball of small radius, right? Now, if you look at this in terms of quasi-self-concordant, this reduces to some Newton sort of method, and you can basically use some accelerated Newton's method, which is solving weighted linear systems. And they also have this extra step in between, which they call their Monteros-Feiter oracle, where they want some step size that's related to the solution and the smoothness of it. So that's some sort of binary search, and involved with weighted linear solves. So maybe it's still not clear how exactly these two are related. But if it can be shown that this is pretty much related to the ball oracle thing or almost similar to that, we could directly maybe incorporate their lower bound, I guess.
Okay, cool. Thank you.
Okay.
So,
yeah.
Last chance for people. Otherwise, let's thank the speaker. There's a little button. We can get a clap going.
Oh, thank you.
Thank you very much. And I don't know, Deeksha, if you're planning on sticking around for a couple of minutes. In general, I guess people can use this table lounge feature afterwards if they want to chat on little video calls.
Okay,
so I encourage people to do that.
Okay. How do we get to that though?
I think Ming is going to shut down this main session, and then we'll just all automatically end up over there.
Okay, yeah, sounds good.
All right, thank you.
Thank you.